Hello everyone and welcome to Signal Systems and Signal Processing with Wolfram U. This lesson will be on Butterworth filter. Analog filter design usually begins with the specification of the desired frequency response for the filter. And the filter specification usually requires the determination of the desired passband and stopband frequency ranges and the gains or attenuations in each of the bands. The specification is used to compute the transfer function of the desired filter. There are four classic families of filters: Butterworth, Chebyshev 1, Chebyshev 2, and elliptic filters. Looking at the magnitude response functions of each of these family types, you can see that the Butterworth filter is the smoothest among all. It has no passband ripple. The passband is flat and smooth. And the elliptic filter has the sharpest or the fastest roll-off, but it's not ripple-free. The Chebyshev filter type has faster roll-off than Butterworth, but it's not as fast as the elliptic curve, and it is not ripple-free. The Chebyshev 1 has ripple in passband, and Chebyshev 2 has ripple in the stopband. In this lesson, we focus on the popular and widely used Butterworth filters. The magnitude squared response of a low-pass Butterworth filter is given by the formula shown here. The frequency omega c, where the magnitude spectrum of the filter is equal to 1 over square root of 2 or equivalently 3 decibels, is the cutoff frequency. The parameter n, which is the order of the filter, determines the width of the transition region, as you see in the plot of the magnitude spectrum for different values of n. Butterworth filters have low complexity and they are suited for many filter design needs. The typical filter specification gives the corner passband and stopband frequencies, omega p and omega s respectively, and the attenuations or gains in each of the two bands, AP and AS, as shown here. For example, consider a low-pass filter with passband and stopband edge frequencies at 500 Hz and 1500 Hz. Also, let's assume that the desired passband and stopband gains are as given here. These gain values, also known as attenuations, are usually specified as positive decibel values. With these specifications, we can put together the transfer function using the function Butterworth filter model in the Wolfram language. Here we show the frequency response of the model. Given the filter specification, we can calculate the order of the filter, the value of n, using the formula shown here. Also, given the value of n, the stopband gain gs, and the edge frequency omega s, we can find the value of the cutoff frequency using the formula shown here. And finally, knowing the filter order and the cutoff frequency, the transfer function of the low-pass Butterworth filter can be obtained using the formula shown here. The poles of the system transfer function are uniformly distributed on a semicircle of radius omega c in the left half S-plane. Also, we call the denominator of the system transfer function the Butterworth polynomial of order n. Let's look at the locations of the poles of the transfer function of the Butterworth filter for different values of n, the order of the filter. Using the Wolfram language, we list the transfer function of the Butterworth filters of order 1 through 5. And here we show the location of the poles for each of the orders. As an example, let's calculate the Butterworth filter poles for n equal to 3 and cutoff frequency omega c equal to 1. And let's find the transfer function of the Butterworth filter. Using the Wolfram language, we have the 3 poles of the transfer function and the transfer function itself. And here is a plot of the magnitude and phase spectra for the filter. Let's also look at the step-by-step solution. Using the formula for the poles, we can find each of the 3 poles. And using the values of the poles, we put together the Butterworth polynomial of order 3. And the Butterworth transfer function can be obtained as shown here. And the frequency response is shown here for the Butterworth filter of order 3. Given the transfer function of a normalized filter with cutoff frequency of 1, we can get different types of filters, low pass, high pass, and band stop, using a simple frequency transformation, as shown here. Let's use the Wolfram language to plot our 4 different transformations of the normalized Butterworth filter. As an example, given the normalized low-pass Butterworth filter shown here, let's find the transfer function of a high-pass filter with cutoff frequency equal to 2 radian per second. Using the Wolfram language, starting with the original transfer function, if we apply the transformation s going to 2 over s, we get the transfer function for the high-pass filter. If we get the body plot of the 2 filters, you can see that we have a high-pass filter. Once we have the transfer function of the filter that we're looking for, to implement it, we need to select the appropriate circuit configuration and calculate the values of circuit components such that they will give us the transfer function that we're looking for. For example, for the Sallen-Key low-pass unity gain configuration shown here, we can find the transfer function as indicated here. And so the Sallen-Key circuit can be a good choice for implementing any second-order section of a low-pass transfer function. If we use the Sallen-Key circuit to build a low-pass Butterworth filter of order n equal to 2 and with cutoff frequency 1000 radian per second, which will have the transfer function shown here, to find the values of the circuit components, we set the transfer function of our Butterworth filter equal to the transfer function of the Sallen-Key circuit. And that will give us a set of 2 equations with 4 unknowns, which means that we need to select 2 of the unknowns and obtain the other 2 by solving the set of equations. Choosing the values of the 2 capacitors C1 and C2 as shown here, we can solve the set of equations for the resistor values. Choosing standard resistor values close to the values that we obtained, we get the transfer function of the filter that we were looking for. Once we have selected the circuit architecture and calculated the values of the components of the circuit, it is common to run simulation tests before building the actual circuit. And after building the physical circuit, again, the circuit can be tested using standard laboratory techniques and instruments. In this lesson, we went over Butterworth filter design and showed that given a normalized low-pass Butterworth filter, we can apply certain frequency transformations to get other types of filters, for example, high-pass filter, band-pass filter, and so forth. Finally, we went over examples of selecting circuit configuration and calculating the values of the components of the circuit.